a new video on my latest project to build a very high energy pulse dye laser. And the project is pretty complicated, and so I've decided to break it up into several phases. The first phase was to buy a couple of used medical pulse dye lasers, flash lamp pump dye lasers. And I obtained a couple of them for very low cost because the units were damaged. The power supplies were no good. And when I took delivery on them, the idea was to convert these to laboratory use, or at least one of them, and then afterward convert or upgrade this to produce substantially higher energies, higher powers. And then the final stage is to part out some of the components, some of the pumps and the electronics, to allow me to produce a far more powerful freestanding laser to see what kind of ultimate powers would be possible. So I've completed the first part of this project, which was to take this existing laser, pull out a lot of the medically related and, for my purposes, unnecessary equipment like an isolation transformer that weighs a good 25 or 30 pounds. Don't need that in my lab. Additional inductances, which I'll get into later, that just slow down the pulse. It's necessary clinically, but it isn't necessary for a lab laser. I've ripped a lot of the control boards, the regulating boards, the things that make sure that when a doctor wants to give 1 joule of energy, they give exactly 1 joule of energy, and that maintains the dye at a certain temperature, and all these other controls that are not really necessary if you're going to be using the laser for purposes of just making bright light. Once I've removed all of that equipment, I then decided what I was going to do is get the unit to operate properly, and whenever possible, incorporate components that would be upgradable. So that's why you see the power supply was replaced not only with a unit that made the 2 kilowatts or the 2 kilojoules per second for capacitor charging, but a unit that can make as much as 6,000 watts for capacitor charging. That's why the huge Variac hooked up to a much more high-powered power supply. This will be compatible with all 3 layers of my project. The dye lasers have fallen out of some favor in the medical community over time simply because they're bulky, they're inefficient, and the compact, lightweight, solid-state lasers have moved into their market. Nevertheless, they do have a market niche. It still remains because of the fact that they produce a fairly usable wavelength of light in the 580 to 600 nanometer wavelength. And because it's pulsed, that wavelength, which interacts with hemoglobin, allows the doctors or the clinicians that are using these to treat abnormal vascular abnormalities in patients. So for example, you expose the skin to a pulsed charge or a pulsed output from one of these lasers, and the light interacts with the hemoglobin in capillaries near the surface of the skin. And that heat is transferred from the hemoglobin to the inner walls of the capillaries, causes protein denaturing or coagulation, and essentially closes off those abnormal capillaries. And therefore you can treat things like port wine stains or telangiectasias, or even treat warts, because warts depend on a capillary bed to supply them with food. You close off the capillaries, you starve the warts, you can treat warts with these lasers. Bottom line is, though, you need a pulse, and the pulse cannot be too slow, otherwise the heat distributes too deeply and too far and doesn't really damage what the target tissue is. It just causes a generalized burn, so that's not useful. And it can't be too fast like a Q-switch laser, because all that ends up doing is heating the hemoglobin to the point that it vaporizes or explodes and doesn't transfer the heat to the tissue that you're trying to treat. So these lasers are operated at about a 1 millisecond pulse duration, which is optimal clinically, but is on the ragged edge of what a pulse dye or what a dye laser is able to operate at. Only the xanthine dyes, such as rhodamine, have been found to be efficient enough that these dyes can actually still laze in the 1 millisecond time regime. And as a consequence, these lasers have to use a tremendous amount of energy. This little tiny machine stores up to 2,000 joules just to get about 2 joules of output, because again they're operating at a regime that the dye doesn't want to operate in. Dye lasers are remarkably robust lasers. They've been around for a long time, and the dye laser gain material, the xanthines or the coumarins, have a tremendous amount of gain. They're inexpensive. The dye that I have here, I could make a liter of it for about $5. Has very high gain. It's tunable. I can cover the wavelength range from the red to the blue. Even with one particular dye, just rhodamine 590 or rhodamine RG6. I can generate a wave band so wide that I can tune it over 10 to 20 nanometers with just using the right cavity optics. Inexpensive, it's self-healing. If I over-energize and throw tons of power into it and cause cavitation, within a millisecond it's repaired. The cavity, the crystal, the gain medium, doesn't require complicated growth and polishing and coating. You put it in a clear tube of glass or quartz, you put windows on the end, or in some of these medical lasers, you actually take the cavity optics, the mirrors themselves, and seal up the ends of the tube, so you don't even need windows. And because the gain is so high, you can use relatively poor optics. The alignment can be kind of lousy and it still operates. The output couplers from these vary from about 15% transmission to about 50% transmission. And so they're very robust in a whole bunch of ways, but there's one big problem with them. And that is that the organic molecules that make up these dyes have loosely bound electrons. They're called the pi electrons. And these electrons, which are in pairs, are stimulated by the photons, the energy from the flash lamp. And when they're excited, they absorb some of that visible light and then spontaneously will decay and produce either incoherent or, if stimulated, coherent laser light. Because those electrons are in the same energy level, they're in opposite spin states, the Pauli exclusion principle. And so when stimulated and they remain in an opposite spin state, they can decay very quickly. That's the spontaneous state that produces the laser output. That state exists only for a couple of nanoseconds before it will decay spontaneously. However, sometimes when the photons are absorbed, one of the electrons will be stimulated to a parallel spin state. It'll be elevated and become parallel with its neighbor. It can't fall back without flipping. This state is far more difficult to decay out of. As a matter of fact, it doesn't even produce photons when it decays. It produces phonons, which are vibrational transmissions or translations. It heats the medium. It decays thermally. And it takes a long time to do it, on the order of many microseconds or milliseconds, orders of magnitude longer than the singlet decay. As a consequence, the triplet state robs the singlet or the ground state molecules from photons that could produce the singlet state, the usable state. So it decreases the amount of photons available for that stimulation, but then it also produces a species, the triplet state, which is absorbent to the output from the laser. The singlet fluorescence is absorbed by the triplet state molecules, in addition to the fact that it's also taken away some of the stimulating photons. And because that triplet state remains around for such a long time, during long flash lamp pulses of many microseconds or milliseconds, the triplet state builds up to the point that it actually terminates the laser action. And so you don't want the triplet state around, but you can't help it. It's created at the same time by the same photons that produce the singlet state. You can add chemicals, oxygen from the air, or COT, which is cyclooxytetrine, and they will induce or enhance the thermal fall of the triplet state. But still, the most effective thing you can do is to speed up the flash. The more quickly you can get the energy in, the more favorable the interaction is to create singlet state energy state that is going to produce the laser. So if you can shorten the pulse enough, you can overwhelm the triplet molecule population with the singlet state population. And that's why with, say, nitrogen lasers that are used to pump in 4 or 5 nanoseconds, you don't even need mirrors for those dye lasers to create output. They'll output with simply the input of some very, very fast ultraviolet light. Similarly, I have a laser scope that uses a KTP, which is Q-switched. in 300 nanoseconds, short enough, the triplet state doesn't build up a lot, and that conversion of green into dye laser output is almost 50% efficient. So if you can get fast enough, these lasers become remarkably efficient. The problem is flash lamps don't like to pump that fast because if you try to put a tremendous amount of energy into them very quickly, they explode. And so there's a trade-off between how hard you can drive the flash lamp and the gain of the laser. And that's why one of the biggest upgrades that this laser is going to have is to increase the pumping speed of the flash lamp. Enough theory. The engineering of the laser here. Just to give you an overview of what's going on, so if you ever bought one of these things or you thought about building one of these things, you can see sort of how the systems operate. There's effectively two plumbing systems here. One is an Iwaki pump that pumps deionized, with a deionized filter here, pumps deionized water through a radiator located at the bottom of the laser, and then from the radiator up to the head, which I'll show you on the other side, back down to the reservoir, which contains the DI backup supply, and then back through the pump again. So that's the cooling loop that cools the flash lamps. Both of the flash lamps are surrounded by a jacket of water and are cooled by this system here. This motor pumps the other plumbing system, which is the dye, and I'll show you on the other side so you can get a view of that. The dye is kept in the same reservoir as the DI water. It looks like the same container, but it's got a small divider between the two of them. It's kind of a neat piece of engineering here. Same reservoir, but two compartments. One compartment contains the dye, the other one on the other side contains the DI water, and there are a couple of fill plugs there that make it easy for you to replace the liquids. In the dye side of the pump, dye side of the reservoir, the fluid is pumped out of the reservoir through a secondary pump. This pump here then sends the fluid through a bubble filter. This 1 micron filter here is not really so much a particulate filter and certainly doesn't remove any of the dye, but removes some of the micro bubbles from the dissolved gas so that you don't get diffraction or sort of a fuzz or a fog inside of the laser tube. Then up through this high pressure line into the bottom of the head, out of the head to the radiator, which is fan cooled, and back to the reservoir again. These are the cooling tubes for the flash lamps. And effectively, because they're going through the metal components, cool the outside jacket that has reflective material on the inside of it. The two flash lamps, the two parallel flash lamps, are pumped in a U-shaped circuit. So pump energy goes in one side, bridges across through a wire, and comes back, and then grounds back down to the capacitor. The unusual thing with these lamps is that the studs that come out of the end of them are actually stainless steel studs about 2 inches long, and they are actually wet. The DI water not only contacts the outer jacket of the quartz tube, but actually touches the metal, and that's why it has to be DI water with a very high resistance so that the high electrical energy doesn't just transmit right through the water. That's why DI water is important here. The other thing that you can see on this side is the capacitor. This NWL capacitor, as you can see the reading here, 3,500 volts and 3 1 by 100 microfarads. It's actually 3 capacitors with a common ground. And as a result, you can actually separate them and use them as 3 separate capacitors. And what I'll explain a little bit later is it turns out that this laser is just as efficient using just one cell as when all 3 cells are firing, simply because the additional capacitance only turns out to prolong the pulse, and all of that extra light that's pumping into the laser is doing no good because the laser action is already terminated due to the triplet state. So I found that this laser is actually more efficient by just removing not only the inductor I removed before, but also some of the additional capacitance. The other thing that you can see with this head is that there's no optical supports because the mirrors are actually supported on the ends. You can probably get a good view over here by that little metal housing here. The mirrors, which are plano, are placed in small little indentations in this outer stainless steel block and then held to seal the cavity by a little silicon O-ring that's underneath the mirror. And then these 3 set screws push on a little ring to actually compress the O-ring and align the optics. kind of funky in terms of like alignment, but nevertheless, it works, and it certainly is compact and convenient. Not something though that you want to do, which I had to do, which is to align these things by using a small little hex wrench between these two live electrodes supporting about 2,000 joules in here. Even with a fiberglass rod, it's nerve-wracking, and one of the upgrades is certainly going to be to isolate the mirrors from the head. On top is a bunch of low voltage electronics that just control some of the systems. Most of the hardware has been removed to make it simpler to operate. What I will show you now is basically how the laser works and give you an idea of what the laser output looks like. So if you step back a little bit with the camera, I'm going to turn the laser on. And first switch I'm going to turn on is going to be, I believe this is the quiet pump. You can barely hear anything, but this is the small Iwaki pump that's pumping the DI water and cooling off the flash lamps. I'm now going to turn on the much louder Procon pump that pumps the dye. You can even see this little tube moves a little bit because it's under much higher pressure. I'm now going to turn on the 12-volt supply that actually allows the trigger transformer to operate and some of the other electronics and the cooling fans. As long as you're here, I'm going to show you the trigger transformer and show you these two little leads that are sticking out of the top of it. The way this system works is that the capacitor, when charged up, is directly attached to the ends of the flash lamp. But the voltage that it holds, up to say 3,000 volts, is insufficient to cause the lamps to arc. What they do is on the anode side, they break the line up and they send the line across the secondary winding of this high voltage trigger transformer. So this is series injection triggering. What then happens is, when a small pulsar that's located up here generates a low voltage pulse, it sends the electrical signal to an LED, which through an opto-isolator to here on the board, triggers a 240 volt pulse from a small capacitor into the primary winding of the trigger transformer. This then steps up 100 times to 25,000 volts and is added to the potential across the flash lamp to now 28,000 volts, which is enough to cause the flash lamp to begin discharging. And then the rest of the current can then flow from the capacitor. It only requires about 700 volts at that point to then discharge the capacitors. The problem, the advantage is that's nice and it's triggered and it fires when you want, is that there's a lot of inductance in the secondary winding here, and as a consequence, that inductance means that it slows down the output, and that's one of the downsides of using this and keeping this, but it's so convenient I'm going to keep it for at least the first two stages of this project. Now I'm going to open up this dump switch. If you look and you'll see this little rod here will move up when I hit this switch. This no longer is now grounding out the power supply and will allow current to fill the capacitor. If you turned off the unit, that would just by default fail. It would close the switch and it would very quickly through these high voltage resistors dump the capacitor and make it safe to use. So we'll open it up again, and now what I'm going to do is I'm going to turn on the trigger pulse, and you'll see a little LED light every time it's sending in that little voltage, that high voltage small current to the flash lamp. You can hear a little click, and that click is the arc going through the lamps, although it's so low power you can't see it now. Now what I'm going to do, I'm going to move this detector out of the way for now so that it's not going to occlude the beam. And then what I'm going to do is I'm going to start throwing power into the unit by energizing the variac, which is what I just did. Now the variac is on. I'll turn this so that whenever you want to, you can see the voltage that's going through and being stepped up here. This is a 10 kVA variac. As I raise the voltage here, you'll see through a voltage divider that's actually 254 volts because it's reading 1,000th of the voltage across the capacitor. And as you see that number going up, this is the voltage across the capacitor. We're now at nearly 500 volts. When you get to about 700, as I said, you'll start to hear a louder click, and you'll now start to see the flash in the flash lamps. But we're way below threshold, so even though a little bit of light may be visible from just the incoherent fluorescence of the dye, there's certainly no laser output. As I'm continuing to raise the power here, you'll see that the voltage continues to rise. And what I'm going to do now is I've turned the oscilloscope on, and you'll see that each time this fires, you'll get this spike. The spike is just due to induced current in the, or induced voltage in the line that's running from the detector to the oscilloscope. That's not actually coming from the photodetector. I'm continuing to go up on the voltage, and we're now at about 1800 volts. Still below threshold, but you can hear the click getting louder, and you can also see the flash getting brighter. When I get to about 120 volts here, which represents about 3,000 volts across the capacitor, you'll begin to get some lasing. And it'll happen at about the center of what you see as the bright spot on the white screen. And it'll have an interesting pattern. You see it's a ring, and the reason that occurred is simply because the dye is absorbing the light coming from the outside of the tube. And with these plano-plano optics, the highest intensity of light is right at the edge, right below the dye cell wall. And so you get this whispering mode around the edge. As I increase the energy, what will happen is more and more of the light will penetrate deeper, and so the threshold will reach deeper into the cell. Eventually, that circle fills in, and then the lower loss center becomes actually more favorable, and you'll get the bright spot that you see there. Hopefully we're not blowing out the camera.
Yeah, the camera actually isn't seeing it. It's just not even there.
Oh, because this is so fast.
Yeah.
That what's happening is sometimes, are any of them appearing?
Well, the after image of the, the bright area is appearing, but the actual laser is not appearing.
Really?
Yeah.
Oh, that's fascinating. Because it's brighter than hell in here.
Yeah, I know. It's not there at all.
Really? You can't see it at all?
No.
Okay. Interesting phenomenon. I don't know how much of that we continue to leave in. We'll see what the editing shows. But you can't see the laser output with this digital video camera because the flashes are so fast that apparently the chances of the read on the camera at the same time as the flash occurs is so low that after about 50 flashes, we can't see any of the images of the laser. And it's amazing because here I'm still seeing after images looking at the screen even now, and the camera shows nothing. So what we'll do is we'll take some still pictures with a camera that we can leave on for a quarter of a second so we can pick up the shot of the laser, and then some of the description I give you with the annular image as well as the filling in the spot will have a couple of images of that so you'll see them in fixed mode. What I can show you though is what the oscilloscope shows when the laser is working. So what I'm going to do is I'm going to put in front of the laser this integrating sphere. Small as it is, it's actually an integrating sphere with a small photodiode at the bottom through a pinhole. I'm going to place it in the beam of the laser, and the output of this thing is hooked up via this cable to the back of the oscilloscope over there. Now what you're seeing each time you hear the click and then you see the pulse on the screen is the induced current from the pulsar. That is not the photodiode. Obviously the photodiode is not going to produce a negative voltage spike. That's the ringing as the high voltage going through the flash lamp. But what you can see is if I begin to turn on the power and cause the flash lamp to flash, you will start to see an output from the photodiode. So I'm going to turn up the voltage now, and you'll start to see and hear at the same time the click and the output of the flash lamp. That pump following the trigger, and you can see we're on 100 microseconds per division, means that there's about maybe about a 20 microsecond delay before the power begins to discharge through the flash lamp, and the light begins to appear. We're still not lasing, we're still just producing incoherent light. But what you'll see is that when we do reach sufficient power that the unit begins to laze, we're going to get a distinct change in the hump that follows the trigger. Now you hear the click getting louder because I keep turning up the voltage. And pretty soon we'll probably start to see a telltale peak. And it's that secondary peak that you see in the main peak of the incoherent light. That's the actual laser pulse. And as I turn the power up, you can see that the laser pulse continues to grow and begins to fill in as more and more of the incoherent light from the flash lamps is above threshold. Fascinating, huh? And as I turn the power down, less and less of the light is sufficient to drive the cavity to laze. So that's pretty much it for this part of the project. I'm going to turn on the safety dump so nobody gets electrocuted. The second part of the project is going to be to make this system far faster because, as I described before, everything that you do to get rid of the triplet state is not going to be anywhere as effective as speeding up the flashes. So part of stage 2 is building far faster capacitors. I'm partway through a Marks bank over here. The flash lamps, the spark gaps, and the coaxial capacitors and the inductors to allow me to produce much higher voltages with the same energy and hopefully produce much faster flashes through the flash lamp. These should overvoltage the flash tube, and I would probably use the series trigger transformer just to initiate the first spark gap and erect the Marks bank. The other experiment that I'm running is this cell over here. Did a little practice machining, seeing if I could produce a water jacket that's sealed properly, and I did. Using Delrin or Teflon, you're compatible with both DI water and methanol. And the flash lamp in this case is the exact same flash lamp that is used in that unit there as a typical flash lamp. It's actually, as you can see, a little bit of the devitrification of the quartz. It's a tired flash lamp. It's been around for a while. But what I'm going to do is, based on an article that was written from the National Ignition Facility, they apparently are finding that these flash lamps, when surrounded by an incompressible water jacket and a very heavy Pyrex or quartz tube, have higher explosion energies than most of the literature that's out there. And so it may be possible to run these lamps much closer or much higher powers than people originally thought, much closer to what was anticipated to be the explosion energy, and still get decent life out of it. So the experiment with this will actually be to blow up this flash lamp and determine how much energy actually does that. And so I'm duplicating what would be happening inside of the laser without actually exposing the laser components. This, because it's going to blow up, I'm going to do outside and should be a pretty spectacular experiment, and that'll be part of the next video. So I hope you've enjoyed this so far. It was fun doing it, and look forward to seeing you next time. And as a little postscript, people have asked often why the cameraman seems to do such a good job photographing these videos. He's got a bit of a background in the same sort of science, and you can see this is his project table here. Just thought you might find it kind of fascinating. Runs in the family, I guess. Thanks.